Okay, so hello everyone. For today's class, I would like to just finishing some subtopics regarding the eigenvalues and eigenvectors. And before we start to have some examples on how to get into the what is actually eigenvalues and eigenvectors, let me give you some analogy. So let's consider a 2 by 2 matrix. For example, we say that the matrix has a 3 minus 1 minus 1 3, the matrix A, and then we set some factors. Okay, we set some factors, column factor 1 0 and 0 1. And we just try to trial and error what could have this resulting product. So AX1 and AX2, we try to multiply and how it looks like. So I think we could start to take that. So basically we just multiply these two vectors, so or matrix. Okay, so matrix A and matrix X or vector X. So that's right here. That this is going to be a 3, -1, -1, 3. Let's say multiply with the x1 which is 1 0. So if we try to multiply, this will be 3, right? 3 for the top, and for the bottom will be -1. Okay. And how about the second one? If we try to multiply, let me write again. Okay. So if we multiply, this will be sorry, it should be 0. It should be 0, 1. Okay. So it should be -1, and then the other one will be 3. Okay. Okay, this is just a normal matrix. But how about if we try, let's say we have another x3, which is 1 1. Okay. So let's multiply. Okay, so we have 3 minus 1 would be 2, and the other one is -1 plus 3, okay, which is 2. Which this could be, we can factorize the scalar number, which is 2, and it is going to be 1 1. If we try with another, for example, let's say a column vectors or column matrices. Let's say the other one is 1 and -1, for example, like that. And if we multiply with the same vector A, and you get that this will be 3 plus 1, 4, right? And the other one is -1, -3, which is -4. And again, we could factorize the scalar, which is 4, and you get that the matrix or the column will be 1 and -1. Now you see especially this one, the third and the fourth, if you see what we have here, this is actually the same matrices or the same vectors as we defined as in the beginning. Okay? This is also the same with the x4. Okay? So there are some special values and special vectors or matrices that when we multiply, there will be a multiplication of that factor itself, and we call these vectors will be the eigenvectors. And this value here, 2 and 4, this will be eigenvalues. And I think 2 by 2 matrix, easy to describe, easy to visualize in paper rather than the 3 by 3. So I hope you get the idea first. So if we try to visualize in terms of graph, if we want to make it into graph, let's say we have here is the x1 and x2, or let's just say xy axis. So if we say the the first is 1 0, so x1 will be 1 0. So let me just describe here. So 1 2 3 1 2 3 or 4, and this is 1 2 3 4 1 2 3 4. Okay, so if we describe, the first one is 1 0, so 1 here and at the 0 for y, and then the other one will be here. Okay, this is the beginning, okay, the beginning of the vectors, the x1 and x2. And then if we multiply, the result is 3 negative 1, which is here, 1 2 3 here. So we'll draw with this different color, and the other one will be negative 1 3, which is here. Okay, so this is the ax2, this is the ax1. Okay, and if we multiply the x3 is on the sides here. Let me write with the red color. So this is the x3, 1 1. Okay, the result is 2. Okay, the result is 2. So let me add 2 is going to be here. Now this condition is what we call, we get the eigenvalue and eigenvectors. Okay, this condition. And one more, just to see how it looks like. The 1 negative 1 is going to be 1 negative 1 is maybe going here. So this will be the next one. Okay, all the small arrow means that this is the original vectors before multiplications. Okay. And the longer arrow will be the after we multiply. And then this will be 4 4. So maybe 4 4 is going to be here. So I will extend the direction. Okay. So these two cases, this will be conditions where we get the eigenvalues and the eigenvectors. So we are multiplying something, and the result is actually scalar multiplication of the vector itself. Okay, so that's the idea, the eigenvalues and eigenvectors. So let me just write something here just to make it simple. So the k, let's say k for this case. K is a vectors, and lambda k. So for special vector, we call the eigenvector. So we assume this works for, or we get that when it is equal, this is for special value, or we call the eigenvalue. And usually we state the eigenvalue as lambda. Okay. And previously, let me just go a brief here. We state that this is a negative. Okay, this is a negative. Not a negative lambda identity multiplied by k is 0. Okay, so if we write here that the ak, let me just write here, and this is lambda I k, then we could rewrite this. Let me just rewrite all the formulations. This should be 0, and there are mainly two cases. So case 1 is basically if k is 0, which is if k is 0, we doesn't really get anything, right? I mean, we want to observe this. Right? we want to observe this, we are trying to get into the eigenvalue, okay? And if the k is already 0, then we will not get anything. So I will write here, not interesting, or maybe meaningless. And case 2 is we are going to have k is not 0 and the determinant of the a minus lambda I will be 0. And this will be our important point. So determinant of this will be 0. We are going to see how it looks like, but let me just write this first. And then we say that let me write here, the a minus lambda I, this is singular if or not if, means it maps some factors to 0. Oh, sorry, this is determinant. I forgot to write determinant. Determinant, sorry. It should be, okay, sorry. I forgot to write this is determinant. Oh wait, it's already correct. Why I'm writing determinant? Sorry. This is the same equations. And then the determinant is here. Okay, this is determinant. Okay. And then this determinant will be this will be, we call the characteristic equation. Or if you could imagine, at least maybe 2 by 2, it will have some. So for example, if we have something on this a minus lambda, something number and lambda becomes our variable, you could imagine that if it is the determinant 2 by 2, it will multiply by itself minus the other part, right? So at least we are going to have a quadratic equation, at least, okay, or more. Okay? So this will be we are going to expect that this is going to be a polynomial equation with roots is the roots will be the eigenvalue. So we are expecting to get the polynomial equation. We solve the polynomial and the solution will be the eigenvalue. So we are maybe there will be 2 eigenvalue or 3, depends on the polynomial. If this is polynomial is cubed, then we'll be having a 3. If that is quadratic, we have 2 eigenvalue. But also it depends. Sometimes maybe the roots can be repeated roots. It can be distinct root, like similar to what we have in the differential equation in engineering math 1. So it could be like many options, but we are going to see later. Okay. But let me just go through this part first. Okay, so basically we are going to have the polynomial equation. And if you remember the determinants in vectors, if you perhaps learned vectors before, I also forgot whether I have teach you or not this one, but the determinants, let me write here, some notes here, that the determinant, it's actually measures the volume unit, or in 2 by 2 is the area, unit cube after all sides are mapped through A. let's say we have example. Let's just take the 2 by 2, easy to draw. Let's say we have the simple 2, 1, 1, 2 matrices. Let's say it's matrix A. And of course, if we take the determinant, this will be 4 minus 1, it's 3, right? Now, if we try to compute in more detail in visuals, this is actually, let me just write here, this is let me write here 1, 2, 1, 2. So let me describe all the vectors. So first is this vectors here. So perhaps this is 2, 1 first here. Okay, that will be. And then let's say this is the variable 1 and this is variable 2. Or you could say xy if you want to xy. And the second one is 1, 2, maybe here. What the determinant actually about is we are going to map another one here, the same vectors with the blue one, the x1, okay? And the other one will be the same as this one. Okay. The same with 2, 1 and 1, 2. Okay. And basically, the area will be, we call this is the determinant A. So this is equal to the area of parallelogram. I think I've taught this before. So the area, so if you have two vectors and you want to compute the determinant of the two vectors, or perhaps if you draw the vectors and you want to compute the whole area here, you could use the determinant and you can take each one of the vectors and take it into the matrix and make it a determinant. Okay, so you could just take this 4 minus 1 is 3. But anyway, long story short, the determinant will be the area of parallelogram. What eigenvalues do when we multiply with it is actually we make it singular. We make it 0. What's happened? The only possible way for this the area to become 0 is, you see, you get it in visuals. So the idea from this, okay, we have this to make it 0. Okay, that's why in this way here, where's my, oh here, in this way here, we have the same inline parallel. So you get the eigenvalue and eigenvectors, okay, from that perspective. So we actually the question is why it should be 0? Because that is the only possible way that this vectors will be equal with this vector. Okay? It will be parallel. Okay. Okay. Because I think it's why I try to teach through the picture, because I think it's easier to visualize that you can get, oh, that is eigenvalue, that is the eigenvector. Sometimes in textbook, they doesn't really mention what it looks like and maybe just giving you words. But I think some simple stuff like this maybe make things easier to visually understandable. Okay? So that's the eigenvalue and eigenvectors. Okay, the next after this part here, so this is one page I dedicated for explaining what is eigenvalue and eigenvector really are through some simple visuals. The next part of the lecture will be finding some eigenvalues and eigenvectors in practice. Okay? So for example, we start with 3 by 3 matrices A. Okay? So basically, what we want to do is we are trying to get into the determinant formulations. Directly, we can write A minus lambda I equal, and basically we state all the diagonal matrix with A minus lambda, or in this case, all the diagonal matrix, we are going to have or substitute with this. Okay, so we take the determinant, let's write here. So this will be 1 minus lambda, the same. This will be -1, negative lambda, 0, -2, and let me make a space over there, and -1, negative lambda. And we want to make this determinant, again, to make sure that we get the eigenvalue and eigenvectors, it should be equal to 0. And of course, if we have 3 by 3, we are expecting to have at least 3 factors, right? 3 roots from polynomial, right? So if we have 3 roots, then I think maybe if you need to Okay, now we can compute this by taking all the important, so first is, let's just take first row, and then this will be, or maybe taking the second row, because it's I've seen 0. So let's say we have -6. This is 2, 1, -1, -1, negative lambda. And then plus, so -1, negative lambda. Or it should be plus, right? Plus. Let me just write like this to avoid mistake, right? And then multiply with 1 minus lambda, 1, -1, we make a space here. Okay, so this will be -6, -2, negative lambda, multiply with -2, so +2. So I think this will be cancelled. And okay, so plus this will be multiply let me write here just to make sure it's correct, or this becomes right. So we have 1 minus lambda squared minus, right? Okay, I think that's good. So minus 1 minus lambda squared plus 1. Okay, and then we multiply that 6 lambda. Oh wait, this should be 12, -2 lambda, so 12 lambda. Okay, let me check again. Okay, so this one is -1 plus 1 will be cancelled, and this will be plus lambda squared and plus lambda cubed. Or we can just multiply with the negative, so we have negative lambda cubed. Or I think just take it positive, I think should be okay. Negative. I think I made a mistake for the signs. Is it true? Negative 2, negative 2 lambda, plus 2, plus 12. Okay, nothing wrong with that. I think this one should be negative. Can you find my mistake? Anyway, suppose that should be this, but I think I will check again later. Okay, I forgot to check. Should be this. Okay, should be this. If you notice my mistake, let me know. Okay, nothing wrong. So 2, 1. Yeah, it should be okay. Oh, should be plus. This should be plus alpha lambda squared. Yeah, okay, good. Okay, now true. Okay, so we can take lambda out, and this will be a normal equations for quadratic equation. Or if you want to factorize, we can write here and multiply with negative. This is what we get. So from here we can take that each one of them are eigenvalues. Okay. Now what's next is we are going to test these eigenvalues, and we need to find the eigenvectors through this. So there are a lot of processes. It's simple, but it takes time to write. Okay? It takes time to write manually. Okay. So first is when the lambda is 0, then we are going to take the a minus 0, right? And suppose that this is identity. And then this is something that we are going to solve by 0. So we have 1, 2, 1. So basically this is the same matrices, because it's we just multiply the 0 and then adding the A matrix, and then we are going to solve this. So we are going to solve this matrix equaling to 0, as we mentioned in previous page. And how to do this? Basically, you can use row operations. Okay? So you can use row operations. So each one of them, we can use row operations. Okay, so basically, we can take this and since we can add the both R1 plus R3 for, let's say R3 will be R1 plus R3, which is going to be 0, 0, 0, right? So we can write that. So 0, 0, 0. And this is also 0. And the 6 for the R2. R1 minus R2. So 6 minus 6 is 0. 12 plus 1 is 13. And 6 minus 0 is 6, right? And then this will be 0. And then the same row 1. Okay. I think we can divide by 13 for the second row. So 0, 1, 6 over 13. And what else? This is, I think we can just compute the first row, and our goal is to make, so besides the diagonal, we should make all 0. So new R1 will be R1 minus 2 R2. So this is 1, 6 over 13, 0, and then this is 1, 2 minus 2 is 0, 1 minus 12 over 13 is 1 over 13. Okay, now after we get this, we can see that from this particular expression that this is going to be lambda 1 equal negative 1 over 13 lambda 3, or let me just write the equations. This is lambda, not lambda, this is k, sorry, k1 plus 1 over 13 k3 is 0, so k1 is negative 1 over 13 k3, and k2 is plus 6 over 13 k3 will be 0, and k2 will be negative 6 over 13 k3. So if we choose, so if we choose k3 is negative 13, then we can get the eigenvectors, okay, for k1 for when lambda is 0, the eigenvectors will be, we can multiply 1, 6, and 13. Oh, negative 13, sorry. So every eigenvectors okay. So every eigenvectors, it will have these 3 values, which depends on the size of the matrix, And it's not over yet. What you need to find is, we need to find all values for each lambda. So let's get into the next one. Okay, and this is again, maybe we need to have like more row operations, and then this is when lambda is negative 4. It means that in our solutions for the row operations, this will be a minus minus 4, so plus 4 identity, and then we need to solve with 0 at the right, as the right equation or the constant. So we need to add all the diagonal. Okay, we need to add all the diagonal. So 1 plus 4 is 5. This is still 6, negative 1, 2, 1. This is negative 1 plus 4 is 3, 0, negative 2, and this is 3. And this will be 0, 0, 0. Okay, I will multiply or let me just write new R3 will be just take sometimes, or perhaps let me just, how about I will write the results and hopefully you can find those. Okay, I will write the rest of the row operation how I did it, but I will just write the results first. Okay, let me just write first the results. This will get you into this. So the row operations, it gives you, I think, simple computation with maybe spending some time to solve. Okay. But as long as you are sticking up to your goal, I think you will get the result. Okay, if you're careful enough and all the computations are correct computations. So we get here, this will be K1 plus K3 equals 0. So K1 is negative K3. K2 minus 2 K3 is 0. So K2 is 2 K3. Notice that to help you define the H eigenvectors, all the operations. So it's supposed to be, usually this is what happened. The below row, the row 3 for 3 by 3 matrices, this will be 0. So we can choose some parameter, because remember, the eigenvalue and the eigenvectors, or eigenvectors, we can multiply with a scalar, right? So this can have a, and actually, how you operate this, make sure that you take all the less variables on the bottom side. Okay. So for example, here it is 0, 0, 0. Take this as bottom. Okay. So that it could be easier to observe. Then when K3 is 1, then we could have K1 is negative 1 and K2 is 2. So we have eigenvector for the second eigenvector. This will be negative 1, 2, and 1. And the same thing for the third one. When lambda 3 is equal 3, with some row operations, again, row operation, I will skip some steps here, just showing you the important value. So by row operation, let me write here row operations. It will result in 1, 0, 1, 0, 1, 3 over 2, 0, 0, 0. Okay. So we have that the K1 is equal to negative K3. I hope you can differentiate the small k. It means that it is going to be the member of the eigenvectors. Okay, so that is maybe the vector itself. And K2 plus 3 over 2, K3 is 0. So K2 is negative 3 over 2 K3. So we could choose some values. Let's say let the K3 is negative 2. Okay, we can get rid of the negative. So we have the eigenvectors. This will be 2, 3, and negative 2. So that's the eigenvalue and eigenvector. Well, sometimes you could also write first, like maybe within this, before we can let the value for K3, we can just write that the K3 is going to be equal to, let's say this is negative K3, negative 3 over 2 K3, and this is K3. And then this is going to be, okay. We can write this first, and then we can let that K3 equal with some numbers, and we can get the whole eigenvectors. So the final form, it could be this, it could be this. Okay, depends on sometimes the direction of the question, but you can pretty much answers in any form, okay, in any form, as long as it is consistent as eigenvectors. Okay. Okay, there are some conditions, okay, for these eigenvalues and eigenvectors, especially for the characteristic equation. Okay. If we can get multiplicity, there will be some conditions, and if we get perhaps some value that's equal. For example, we have this one line, row 0. In some other case, it could be 2 rows that are 0. So that is actually another case, okay, that I think maybe we can add just one more case for the multiplicity. So let me add case of multiplicity. So let me just give you example. So example, this 2 by 2 matrix. So I think it should be simple. So if we take the determinant, if we want to find the eigenvalue, then this will be 3 minus lambda, 7 minus lambda, and then 4, negative 1. So this will be 3 minus lambda, 7 minus lambda, and then this will be minus 4, so plus 4, right? So we have 21 minus 10 lambda plus lambda squared. And then plus 4, so this should be 0. Plus 4 is 17, right? Or no? Okay. So lambda squared minus 10 lambda. I think I will continue this Friday, okay? All right, now okay, the attendance